Reaction mechanisms. Balanced chemical equations indicate the substances that are present at the start of the reaction and those that are produced at the end. They do not provide any information about how the reaction occurred. Up to this point, you've pretty much thought, oh, yeah, these reactants mix together, react, produce these. It's not as simple. The process by which a chemical reaction occurs is called the reaction mechanism. And it's a series of steps that we call elementary steps that make up an overall reaction. Consider the reaction. So nitrogen monoxide plus ozone will produce nitrogen dioxide and oxygen gas. This reaction is the result of a single collision between the nitrogen monoxide and ozone. So it's called an elementary process because there's one elementary step. There's just these two molecules collide, nothing else happens. This is a regular, what you've known up to this point, type of reaction. So if it happens in one step, it's called an elementary process. Each step in a process is called an elementary step. So because there's no other equations, no other steps, this is an elementary process. If the nitrogen monoxide molecule's concentration is doubled, turns out that the rate also doubles. So how do we write that? The concentration doubles, and then the rate doubles. So it is first order with respect to NO. If the number of ozone molecules is doubled, the rate doubles. So now we're talking about ozone. Doubles, we double the numbers, so 2 represents double. And again, the rate just doubles. So it is also first order with respect to ozone. So now we can write our rate law expression. So rate is equal to the rate law constant times the concentration of nitrogen monoxide to the first order and times ozone to the first order. So we can get the rate law expression if we know this is an elementary process. It is the coefficients from the balanced chemical equation. Those are 1, and so these are 1. Here's another example. Nitrogen dioxide decomposes into nitrogen monoxide and nitrogen trioxide, given by this equation. So 2 molecules are needed to collide. If the number of nitrogen dioxide molecules is doubled, so again this is 2, so 2 to some exponent, that's the concentration or mass or whatever, the rate will increase 4-fold. So the rate is 4 times as fast if you double the concentration of your reactant. So M must be 2. 2 squared equals 4. So it is second order with respect to nitrogen dioxide. So the rate law expression is given as rate is equal to K, the rate law constant, times the concentration of nitrogen dioxide to the exponent 2, second order. So again, this is an elementary process. The chemical equation gives us our rate law expression because happens in one step. The coefficient becomes your rate law exponent. So the exponents in the rate law for an elementary process are predicted to be equal to the coefficients of the reactants in the chemical equation for that elementary process. So it's nice to be able to predict rate laws, but really we should do experiments and find the rate laws like we just looked at. Comparing trials and what happens to the rate when you change the concentration of one of your reactants. Okay, let's consider the following reaction. 2 molecules of nitrogen dioxide react with fluorine to produce 2 molecules of NO2F. Now, once you get more than 2 molecules that have to collide, right? They have to collide with the correct collision geometry. They have to collide with the correct activation energy. So there's a lot of factors at play here. The more molecules you have, the less likely it happens in one step. So usually the maximum it can happen in one step is 3, but more likely it's either 1 reactant or 2 reactants. So what do we know about this? We've got 3 reactant molecules, and it actually appears to proceed as 2 elementary steps. So this is how normally the steps are written out. You'll either be given these and asked to come up with a rate law expression, or with a rate law expression, you'll be asked to come up with a possible reaction mechanism. Now, once you have the rate law equation, you can find out some stuff, but you might come up with an alternate reaction mechanism than somebody else, and that's okay. So, when they're written out like this, it's a couple of things you need to know. Anything that appears to be produced in one step, used up in the next step, and is not part of the overall equation is called a reaction intermediate. So do we have any species here that do not belong in our overall? We have NO2, F2, NO2F, and F. This F is a reaction intermediate. It's a product in step 1, used up in step 2, and does not appear in the overall equation. So what you do when you have a reaction mechanism like this is you add it up like we did with Hess's law. Reaction 1 plus reaction 2 should add up to give us the overall equation. So we've got 2 NO2s. We have F2. We have 2 NO2Fs, and those F atoms cancel because they're on the left and the right hand side. So F is our reaction intermediate. Now something else you might have noticed over here on the right hand side, we're told about the speed of reactions. So the first step here goes slow, and the second step goes pretty fast. So the whole reaction can only go as fast as the slow step. You've driven down the road before, and you've been stuck behind a whole bunch of cars, and you can only go as fast as the slowest car will allow you if you can't pass. So we have a slow step, and that is the rate determining step. That is the one that determines how fast your reaction can proceed. Because this part can't happen until we make the fluorine atom. So you can get your rate law expression from your elementary step that is the slow step. So the rate law expression for this reaction will be NO2 to the first order times F2 to the first order, because in the slow step we have a coefficient of 1 in front of NO2 and a coefficient of 1 in front of F2. So those become the reactants in your rate law expression, and their coefficients become your exponents. Okay, so just to recap here, multi-step mechanisms involve one or more intermediates. When chemical reactions occur in steps, often one step is much slower than the other steps. The overall reaction of rate cannot exceed the rate of the slowest elementary step of the mechanism. Since the slow step limits the overall reaction rate, the slow step is called the rate determining step. The overall rate of a reaction is not affected by the rate of any faster steps that occur after the slowest step. Fast reactions that occur before the slowest step matter because they affect the concentration of the intermediates at the slow step. The coefficient from the rate determining step are therefore the exponents in the rate law. Okay, so reaction mechanism guidelines. Each step is elementary, and you can have no more than 3 reactants. The elementary steps must add up to produce the overall reaction, just like we did with Hess's law. And the slow step is consistent with the rate law equation. So the coefficients to the slow step match the exponents in the rate law equation. So keep these in mind when you're asked to make up a reaction mechanism. Okay, so let's consider this information. Carbon dioxide plus 2 hydroxide ions produces carbonate and water. So it's been broken down into 2 steps, and one is slow and one is fast. So always double check to make sure that this is possible by adding up the 2 reactions and then comparing them to the overall reaction that you're given at the beginning. So the reaction intermediate would be the bicarbonate ion, because it is produced in the first step, used up in the second step as a reactant, so they would cancel out and it's not in the overall. So we end up with CO2 plus 2 OHs going to carbonate and water, and that matches the overall. So this is a reasonable reaction mechanism. So how do we get the rate law expression? Look for the slow step, then look for the reactants in the slow step and their coefficients. So the rate law would be equal to the rate law constant times the concentration of carbon dioxide to the first order times hydroxide to the first order. So there's your rate law expression. First order with respect to CO2 and OH minus, second order overall. Okay, so consider this reaction. We've got 2 molecules of hydrogen gas, 2 molecules of nitrogen monoxide gas. So that's 4 molecules that have to line up, correct orientation, correct speed, correct energy in order to make this reaction go. So it probably won't occur in one step. We know that the rate law expression is second order with respect to nitrogen monoxide, but it's only first order with respect to hydrogen. If that coefficient was 2, if that exponent for H2 was 2, then it would come from this step. So we know based on the rate law exponent for hydrogen versus the coefficient, this does not occur in one step. So therefore, this suggested mechanism is not correct. So we know that the slow step contains NO and H2. The coefficient in front of H2 is 1. The coefficient in front of NO is 2. So look for the slow steps. That's the only steps you need to be concerned with right now. So in reaction mechanism 2, our slow step has 1 in front of H2, but only 1 in front of NO. So this one cannot be our reaction mechanism. Reaction mechanism 3, the coefficient is 1 for H2, 2 for NO, so that would work. And if you add up these two steps, the water vapors there, oh, this is what cancels. Here's your reaction intermediate, N2O. So if you add these up, 2H2, 2 NOs, 1 N2, 2 H2O vapor. So this is your reaction mechanism for this reaction. All right, here's one. We've got a potential energy diagram for this reaction. 4 molecules of hydrogen bromide vapor will react with oxygen gas to produce 2 molecules of water vapor and 2 molecules of bromine. So our task is to come up with a reaction mechanism. Now there's hints in the graph. And we know there's 5 molecules of reactant, so this is definitely going to happen in steps. And by the graph, we've got 3 activation energy humps to get over. So this is going to happen in 3 steps. Here's, well, that's a very bad straight line, but here's 1 step. Here's 2 steps, and then the last one is the last hump. So there's step 1, step 2, and step 3. Now, here at the bottom of these valleys will be your reaction intermediates, because they're going to be your products of that first step or that second step. So let's take a guess at this. Okay, I've just moved this over so that we can write beside it. Okay, so the first step has the biggest activation energy, so that's probably your slow step. And we have to have HBr and O2 as a reactant. So we're going to guess what a product could be. So maybe it's HOOBr. Now we know it's going to get used up because we can't go directly from the reactants to the product. So we're going to have some reaction intermediates. And I've just basically incorporated all of the atoms. So this would be one of our reactants in our next step. And we need to use up 4 HBRs, but only 1 O2. So we're only going to use O2 once, but we are going to use HBr more than once. So maybe this one is, makes 2 HOBRs. Now, we've gotten rid of HOOBr, by having it as a reaction intermediate. Now we've produced 2 HOBR, H-O-B-R, so we need to get rid of that, but we need to get rid of both of them. And we need 2 more molecules of HBr. So I'm going to say that the next step happens twice. So HOBr plus HBr. And this will go to H2O and Br2. We're starting to get our products. This has to happen twice to get rid of the 2 HOBRs. So now we have used 1, 2, 3, 4 molecules of HBr, 1 molecule of O2, and this will get canceled, this will get canceled. So we have used 4 HBRs, an oxygen, and we made 2 waters and 2 HBRs. So these 4 steps add up together to give us our overall reaction. So what happens is you can combine this, because there's not 4 humps, there's only 3, so there's 3 reactions. This is just happening 2 HOBr plus 2 HBr. Don't forget, this is just a suggested reaction mechanism. So now I've got 3 reactions. And if that's the case, and the first step has the biggest activation energy, so it's probably going to be a rate determining step, because it takes the most energy to overcome to get that part to go. So rate is going to be equal to K. What are the reactants? HBr, exponent 1, and O2, exponent 1. And it just so happens that doubling the concentration of oxygen doubles the rate, but doubling the concentration of HBr only doubles the rate. So we know that this 4 HBr is not the coefficient. So that's some other information too. So this is basically how you approach your provide a reaction mechanism. Either you've got a chart, a potential energy diagram, or you've got some rate law data information, how the concentrations affect the overall rate, so you can get a rate law expression, which is then your slow step, and you just kind of build around that. So like I said, you may come up with different reaction mechanisms than your neighbor. Okay, good luck.